Okay, this was where we left at this slide. Actually, we have the same slide for reinforcement learning here. Maybe it was a bit unnecessary since we said neuroevolution is commonly used as a part of reinforcement learning paradigm. That's why I guess I added, I don't remember, but it's a bit unnecessary maybe, so I continue. So actually there are other search strategies as well. I mean, neuroevolutionary approaches, these reinforcement learning, and this is what you do basically is optimization here. Optimizing these parameters for this cost function. And the search space architecture will define the constraints for these parameters. So it is in the middle and it's at the heart of this neural architecture search operation. And this strategy is actually the type of optimization you use. So if you want to get to know these stuff, guys, you need to get a proper optimization course. And we've got a optimization course not in our department, but in mechatronics. Halit provides this course. I strongly recommend this course. I also recommend Kemal Hoca's course from METÜ. By the way, Halit was a student of Kemal Hoca, so if you take Halit's course, it's quite good as well. So I strongly recommend an optimization course for those who want to just study neural architectural search, and a machine learning course as well. We have a machine learning course and artificial intelligence course in the computer science department, but before examining it, go and examine Matthew's and Bilkent's courses as well. They've got nice courses as well. So the final step is performance estimation. Guys, let's try to understand, recap what we have done. The first step was the search space. I'm sorry. The first step was the search space. This was a handcrafted space of possibilities of different architectures. The search strategy, the heart of it, was the optimization technique, which have chosen sequentially different search spaces architectures. And this is where you estimate the performance. This is the cost function of the optimization. So the search strategies aim at finding a neural architecture that maximizes some performance measure, such as accuracy on unseen data. If you're dealing with classification, it is the classification accuracy on a training set or a validation set, whatever. It's usually a validation set. So to guide their search process, these strategies need to estimate the performance of a given architecture. They consider it as iteration. So at an iteration, you are considering an architecture A, which is an element of the architectural space, this nice A, and you get the performance estimation for this A. So there's another A then. So what you do is you get this performance. The simplest way of doing this is to train the architecture on a training data and evaluate its performance on a validation data, just like you do. So for each iteration, for each architecture, you complete a whole training, maybe 100 epochs, taking so many GPU hours, just for a single architecture. Then, looking at the performance, you try another architecture. Which architecture? The search strategy chooses it. However, training each architecture to be evaluated from scratch frequently yields computational demands in the order of thousands of GPU days. Because imagine you train the system, it takes 8 hours. Then at the next iteration, another 8 hours, another 8 hours. When you try 30 iterations, you got 10 days. Because a single iteration is just 1/3 of a day, 8 hours. So it takes so much time. This naturally leads to developing methods for speeding up this performance estimation. So basic performance estimation is the simplest way of doing it, training the architecture and estimating at the validation data. But it takes so much time. So at this step, we're going to consider different novel methods of doing this thing faster. Okay, how to do this thing faster? Actually, in this nice paper, guys, actually we've seen this. This is the paper just provided you here, Neural Architecture Search. This paper, they categorize, they scrutinize the possible ways of performance estimation or speeding up the performance estimation. And they analyze the speedup methods for this step, speeding up this step. They have 4 titles, and actually they explain these 4 titles in a table. And they provide references for these tables. And if you just check clearly, all the references are extremely new, guys, within a few years, because this field is new. This is the future of deep learning. We are trying to find the next step of deep learning. Okay, what are those methods? We'll start with the first one, the lower fidelity estimates. By lower fidelity, we mean somehow making the fidelity of this training lower. So we do not train them for 100 epochs, we train them for 10 epochs maybe. Or we don't train for the entire training set, we train for a smaller set. Or we don't train them for at the highest resolution, the given resolution, we train them for a lower resolution. Or with less filters, with a smaller architecture, wherever we come, we change the architecture a bit, we train a little part of them. So we lower the fidelity at some level, at the training level, at the dataset level, or the architectural level. So we do something. Okay, it will speed up the process because it will make one iteration not 8 hours, but maybe 1 hour. And it will just make your all iterations just much faster, and this will speed up your process. Nice. What is the downside? The downside with these low fidelity approximations is they reduce the computational cost. Yes, that's okay, but they also introduce a bias in the estimate of performance, which will typically be underestimated. Like what? Like you're using a subset for the training data. Well, maybe you didn't just generalize the training data and you're underestimating your problem. That's a trade-off. Still, when we are doing the speed up, we are doing a handcrafted strategy design here. You're looking at the data. I'm going to take this part of the data because this part of the data will be generalizing the entire training set, and it will help me to find the right architecture in general. This is a handcrafted design. We have done another handcrafted test, but it will just lower the fidelity, but maybe not change so much things. Maybe you can later check things by higher fidelity and compare it, but this way it will be solvable because it won't take GPU days or GPU months. You will complete your job in a week and it will be okay for you. So that's a way of doing it. Doing things in shorter and simpler ways is lowering your fidelity, so this guy will take smaller time and you'll be able to speed up your process. Well, this approach may not be problematic as long as the search strategy only relies on ranking different architectures. The relative ranking remains stable. What I'm trying to say is, well, this search strategy gets different architectures and you're using a subset of the data. If the subset of the data can generalize the data properly, then maybe individual performances will fall because you're using less data, but relative performances between architectures will stay the same. Their ranking will stay the same. In that case, there's no problem because we are trying to find the best architecture. When you find the best architecture, do your training with the entire data and see your real results. You can do it. But if the relative ranking remains stable, that is not necessarily the case. That's the human bias we are talking about. And if you can just show that the relative ranking is okay, use lower fidelity rankings, and it's commonly used, guys, because it's the most simple thing to do. You're just lowering a fidelity of some part of the pipeline, the data set, whatever you're doing. However, recent results indicate that this relative ranking can change dramatically when the difference between the cheap approximations and the full evaluation is big. What does this mean? You're not using the entire training set, you're using a little training set. In a little training set, maybe an architecture will work fine, but another architecture will not work fine. But if you have used the full training set, that architecture would be working better from that smaller architecture. Then this is not the right way to do it. So it's a hard trade-off, guys. And there are nice analysis papers on these guys. If you're interested, read it. And Zella et al. 2 years ago, they argue gradually increasing the fidelity. If it's a training set, do a fidelity, then just make your search space smaller, increase the fidelity again, smaller, increase the fidelity again. So create a search strategy which will encapsulate this lower fidelity strategy and the search space all together so that you reach there in a more confined and safe manner. Nice paper. Just let me show you the paper so you just towards automated deep learning, efficient joint neural architecture and hyperparameter search. Very nice papers, guys. Just I congratulate them because I would really like to write these kind of papers. But with you guys doing nice PhDs and master studies, we'll be able to. Okay, sorry. Let's continue. Let's continue the next speed up, which is the learning curve. So what is the learning curve? In the next video.